So maybe you can talk and see if people hear you.
Testing. Testing.
Sam, can you?
Hello? Can people hear me?
Okay, welcome everybody. Thank you for coming. Today we're welcoming Sam Trachtenberg from the UK. You might know him better by Sammy Uri on YouTube, where he has 60,000 subscribers. Sam designs, or in the past, he has designed efficient piston doors in Minecraft and also built a CPU. And most recently, his biggest accomplishment has been building Minecraft in Minecraft. So a few weeks ago, somebody shared this video in our EdSTEM discussion board, and all the TFs and BOAs were also impressed with it that we decided to invite him to come speak in this CS 121.5 advanced section. So that's enough intro. I'll let Sam take it away.
All right, thank you very much. Welcome to my talk. So I'm going to be talking a bit about how this is possible and how we can recreate a video game within itself in this way. But before that, a little bit of introduction about myself. As Gabe has mentioned, I'm Sam, but I'm mostly known as Sammy Uri online, and I'm 16 years old. And I've been playing Minecraft since 2013, so that's quite a lot of my life. So I would say I'm pretty experienced in the field. So what actually is Redstone? Like, how are we going to be able to recreate video games within a video game? Well, Redstone is essentially the Minecraft equivalent of electricity in real life, and you can use it to construct circuits and build logic gates, etc. So there's quite a few Redstone components, but for building computers, we're really only concerned with these four here, which are in order a Redstone wire, Redstone repeater, the Redstone torch, and the Redstone comparator. So I'll just briefly describe what each of these do. First of all, Redstone wire, to the surprise of absolutely no one, is wire. So it can be off or it can be on, and you can use this to send signals between other Redstone components. So as well, you could do more interesting things with it. For example, you can create branches and circuits. And of course, Minecraft is a three-dimensional game, so we can stack Redstone wires on top of each other and create all sorts of weird shapes like this. And this comes in really handy if we're trying to construct a large complicated circuit, but we want to fit it in a small space, since then we can take full advantage of the 3D aspect of it in order to do so. So then moving on to our first Redstone component, we have the Redstone repeater. And the way this one functions is essentially as a diode, which means signal can only pass through it in one direction. So on the one we have here, this is a Redstone repeater that's facing towards the right. So if we try and pass this signal from the left, you can see it'll flow through it. But if we try and pass this signal from the right, you can see it can't pass through. And repeaters also have one other property called repeater locking. And this is useful when you're building memory circuits, since if you power a repeater from the side with another repeater, as you can see from that gray bar on it, it becomes locked. And what this means is that it'll keep its current state. It essentially becomes a D flip-flop. And so the reason this is used in memory circuits is because since it keeps its state, you can lock the repeater and then continue to read its output even when the input changes. So that's how the repeater works. And our next Redstone component is the Redstone torch. This one's a bit simpler. It's just a NOT gate. And the way this works is that the output is essentially the opposite of the input. So if the input is on, then the output is off, and if the input is off, then the output is on. And there are a couple other Redstone blocks that are also...
For people that are not as experienced in Minecraft as you, what was the original motivation why they introduced these things? I imagine that it wasn't to build computers inside Minecraft.
I can't actually remember. Originally, the only components that existed were the Redstone wire and the Redstone torch. And from those, you could build a NAND gate, which we'll get to later. So technically, it was possible to build a computer in Minecraft from the start. So I think the motivation was to create circuits in this way, but I'm not entirely sure about that. So anyways, can I move on?
Yes, sure.
Right, so there's these other Redstone blocks which are important. First of all, the Redstone block, which is just a power source. It outputs power to everything that's touching it. And the Redstone lamp, which could either be on or off, depending on whether there's a signal flowing into it. And you could use those to create screens or number displays or anything else that requires, visual output. So there's a couple other concepts in Redstone that you need to be aware of. First of all is delay. So time in Redstone is measured in a unit called ticks, which are 0.1 seconds each. And all components have 1 tick of delay, but repeaters could also be set to 2, 3, or 4 ticks. So, of course, in order to minimize the delay of a circuit, you want to try and use as few components as possible, because then you have the fewest ticks of delay as possible. And the reason repeaters being able to set to different amount of ticks is useful is because it can be used to synchronize a circuit. For example, if you have a logic gate, generally you want both inputs to happen at the same time, because otherwise that could cause issues like race conditions, where if it gets inputs at different times, that could just cause problems in the circuit. So that's delay. And then signal strength is another unique feature to Redstone, which specifies how far current can flow from a given block. And the maximum is 15. So for example, if we had this circuit here, you can see we have a redstone block or a power source connected to a very long line of redstone. So right next to the redstone block, the signal strength is 15, but this gradually decreases as the signal moves to the right. And as you can see on the end of the wire there, since the signal strength has dropped down to 0, the wire turns off. So obviously, this is not particularly helpful, since oftentimes you want to create wires that are longer than 15 blocks. So in order to go around this, we could use a repeater. And this is actually where repeaters get their name, I believe, since they essentially repeat the signal and can extend it by another 15 blocks each. So as you can see there, after the repeater, it's bumped all the way back up to 15 blocks. But signal strength also has another purpose, which is for the final redstone component we're going to talk about, which is notoriously the trickiest one to understand. Since not only does it have 2 modes, it can either compare or subtract, it's also the only redstone component that operates based on signal strength. So it's not a simple binary on and off. So the 2 modes are compare and subtract. I'm not going to dive too much into the details since they're not really that relevant, but compare outputs to signal strength A if A is greater than or equal to B, and subtract just subtracts signal strength B from signal strength A. So using all the components that we've talked about, we can create other logic gates. For example, this here is an OR gate built out of 2 repeaters and some wire. And what this one does is that the output is on if either of the inputs are on. Similarly, this is an AND gate, and the way this one works is the output is on if both of the inputs are on. Then we have the NAND gate, or the NOT AND gate, which is the input is off if both of the inputs are on. And finally, the XOR gate, or exclusive OR gate. This is actually one of the few logic gates that can be implemented with comparators, using some tricks of signal strength to reduce the number of gates. And the way this one works is that the output is on if exactly one of the inputs is on. So if they're both on, it'll be off. And this is useful in other circuits, which we'll get to next, such as an adder circuit. Here we have an 8-bit adder, and you can see a couple of XORs in there. It's also constructed out of other AND and NOT gates. And like I mentioned earlier, this is a prime example of how the 3-dimensionality of Minecraft is very helpful, since we can stack each bit of the adder on top of each other and create a very small circuit that still has all the functionality of an 8-bit adder. And similarly, we can create a byte of memory in this way. You can see they've all been stacked on top of each other again. So on the right-hand side, we have a repeater that's being locked, which I mentioned earlier can be used to store its state. And on the left-hand side, we have a comparator on subtract, and that's used to select whether we want to read from that byte of memory or not. Since if we subtract 15 signal strength, the output's always going to be 0, so we can stop it from being read. So that's how we build circuits, and we can gradually increase their size. But of course, the goal here is we want to run Minecraft. And in order to run Minecraft, we need something that can run programs, namely a CPU. So now we can move on to how we design those. So CPUs are generally designed primarily out of these components. We have an ALU, or an arithmetic logic unit, and this is what does all the maths for the CPU and all the bitwise operations and all that. Then we have registers, which are temporary stores of data, input and output, which is used to interface with the CPU. We have the control unit, which controls all the other parts of the CPU and decodes instructions. And finally, we have memory, which stores data and the program. So let's go through each of these in order. First of all, the ALU, or the arithmetic and logic unit. So this one in my CPU does various arithmetic instructions like add, subtract, multiply, divide, and square root. These are pretty self-explanatory. Then we also have bitwise operations, which are essentially the logic gates that I mentioned earlier applied to each bit of the input. So the output would be the AND of the first 2 bits, then the AND of the second 2 bits, the AND of the third 2 bits, and so on. And finally, we have bit shift operations, which are shift left, shift right, and rotate right. And what these do is move all the bits of the input to the left or to the right by a given amount. And this is essentially the same as multiplying or dividing by a power of 2. So these are the actual circuits as they're implemented in Minecraft. And you might wonder why there's 2 different sets of them, since they're all part of the ALU. Well, the reason is adding, subtracting, bitwise operations, and bit shifts are fairly simple conceptually. So they can be implemented with a small number of gates and hence don't take that long to process. Whereas multiplication, division, and square rooting is much slower. For example, if you think about long division, you have to do loads and loads of subtractions per division. So in order to process those, the CPU has to stop for a moment and wait for it to finish processing before continuing. And that's also why they're in a separate circuit, just to make that easier to implement. So that's the ALU, which does all the maths. Now I can move on to registers, which are, as I mentioned, a temporary store of data. And there's 2 different types of registers in our CPU. First of all, we have the general purpose registers, which are those. And these store a byte of data each, and they interface with the ALU, memory, and input and output. Basically, whenever you have data that's being processed, at some point it has to pass through the registers. And you might also wonder why there appears to be 2 identical copies of them. The reason for that is that they both go into separate inputs to the ALU. So for example, if you want to add 2 numbers, it's more convenient to read it from 2 sets of register files than to read both numbers from 1 set of registers. So essentially, we've just duplicated the registers and flipped them like that. Then we also have other registers in the CPU, and these all have specific purposes to them. For example, the program counter is a register that stores where the CPU currently is in the program. The current instruction register stores the current instruction that's being executed. The flags register, which is also known as the status register, stores information about the last ALU operation. So for example, if the last ALU operation was 0, it'll store that information. If it was negative, it'll store that, and whether or not it overflowed, as in exceeded the number of bits available, it'll store that as well. And then that's used in order to make decisions about branching in the program. For example, you can say, if the flags register shows 0, go to this place in the program, otherwise go to the next instruction. And that's what makes the CPU able to run any program, essentially making it Turing complete. Another register. Sorry.
Another question, did you base your design on any particular CPU design any particular CPU design, or it's cobbling together various different parts?
It's more cobbling together different parts, yeah. I mean, I've created smaller CPUs or simpler CPUs before and essentially just upgraded them as I went along. So it's not based on any real life CPU, really. I mean, in the most abstract sense, of course, it's just a generic CPU design, but yeah, I mean, the specific implementation is all my own design. So anyway, the stack pointer is another register, and this one just stores the top of the stack, which is a data structure in memory used for very useful in subroutines. So that's all the registers. Now we have input and output. This part isn't too complicated. We just have 256 input and output ports, and the ones you see there are the 8 that are built into the CPU itself, but you can add more if you need. And these are used for interfacing with other devices, which we'll get to later. And each port sends or receives a single byte of data at a time. And also, since the CPU might not always be able to receive data straight away, for example, if another component is still processing, the CPU is going to wait for it to respond before continuing execution. And you can also use this to, you can use ports to control other circuits as well. You don't necessarily have to send data. For example, you could assign a port to, say, clear the screen. So that's used for controlling other circuits. Then we move on to memory. Now, there's a few different ways that memory can be approached. One way is in von Neumann architecture, for example, programs and data are stored in the same memory called main memory. And this is quite useful in real life, for example, if you need an operating system, because then you can easily load and store different programs to use. But it does come with a disadvantage that you're often having to read data and instructions at the same time from memory. And since we're not going to be running an operating system, we just need to run Minecraft, that's not particularly applicable here. So instead, we use something that's coincidentally called Harvard architecture, which has separate data and program memory. So, and then the data memory stores, or the RAM stores data and addresses, and the program memory stores instructions. And since they're separate, we can therefore optimize each for what its purpose is. So for RAM or data memory, in our CPU, it stores 256 bytes of data. And since it's random access memory, any byte can be individually accessed. But it is fairly large, at least for Minecraft standards. 256 bytes might not sound like a lot these days, but it is a large circuit. And therefore, memory access is quite slow since it has to, travel a long distance around the circuit in order to reach the CPU. So how do we get around that? Well, we use something called a cache. So this data cache, which you can see on the right there, temporarily stores 64 bytes of data. And since it's a lot smaller, it's much faster to access the data since it doesn't have as far to travel. However, it does come with a disadvantage that obviously, since it only stores 64 bytes, there's a chance that the data you try to access isn't in the cache at the time you try to access it. So in this situation, the CPU will have to free up some space in the cache to bring that data into it. And the way it does this is using an algorithm called least recently used, where basically for each section in the cache, it keeps track of the last time it was accessed by the CPU. And whenever it needs to free up space, it gets rid of the section in the cache that was used the longest in the past. And generally, this means that it was old data that you don't really need anymore, or at least not soon. So therefore, the CPU takes that bit of data, sends it back to RAM, and replaces it with the new data that you're trying to access. And this way, generally, the CPU only has to access data in the cache, and cache misses are fairly rare, which is very good. So that's how data memory works. Then program memory is quite different, since first of all, instructions are 16 bits or 2 bytes each, so they're not 8 bits like the rest of the CPU. And they're also stored in a 4 kilobyte read-only memory, which is also going to suffer from the same problem as RAM. 4 kilobytes is a lot, so that's fairly slow. So we use exactly the same trick to get around it. We just make a cache, which temporarily stores 64 instructions, which is 128 bytes. And that's actually the circuit right there. As you can see, it's kind of split into 2 light gray blobs that are identical. And the reason for this is that the first 8 bits and the second 8 bits of each instruction are stored separately. And this just makes it more convenient to decode. As well as that, it's also simpler to build, since 15 signal strength just so happens to be enough to reach across exactly 8 bits. So anything above 8 bits in Minecraft is a bit harder to build. So this way, we keep it nice and simple.
So Sam, there is a question on the Zoom chat.
Let's see.
Are you using, do you implement a higher order data structures such as lists or hash functions in order to use the to build the cache? Or
no. So for the LRU cache, each cache line has a 7-bit register. So whenever you access it, I believe it sets all the bits to 0. And then whenever another cache line is accessed, for every other register, it sets that bit to 1. And what that means is that there'll always be exactly one register where all of its bits are 1. And therefore, you can detect that with an AND gate. And that's the one that was used longest ago, because it means that all the other cache lines have been used since that one was last used. So that is fairly efficient to implement in hardware when you don't have that many cache lines, like 8 cache lines is okay. But if you were to have a larger cache, this system wouldn't really work anymore. So it's just for this specific purpose, that was fine. So, all right, moving on. The control unit. So this is the last part of the CPU. And that's it right there. It decodes instructions and it tells the rest of the CPU what to do, basically. So if you actually look at the circuit there, you can see it's made up of horizontal purple wires, and those store what the current instruction actually is. And then perpendicular to it are vertical wires of various different colors, which are color coded to different parts of the CPU. And they're essentially just a bunch of AND gates that detect whether that control line should be active or not, depending on the instruction. So for example, an add instruction, which adds registers B and C and stores in register A, would activate the read register B wire, the read register C wire, the add wire to add them up, and then finally the write to register A wire to store the result. And so we can assemble all of these components together, and we get an entire CPU, which I've called the Chungus 2. So yeah, don't question the name. Now, of course, we have a CPU, but we want to be able to program it somehow. So CPUs don't directly understand high-level languages like Python. So instead, we're going to program it in something called assembly, which is a very low-level language. And essentially, each assembly instruction corresponds to one thing the CPU does. For example, it could be an addition, it could be a memory load, it could be a branch, it could be a halt. And but the CPU can't process text like this, of course, so we have to feed it through a program called an assembler. And what this does is it just takes each assembly code instruction and it maps it into one machine code instruction. Now, machine code is basically the same thing as assembly, except it's in a binary format, so the CPU can actually understand it. And so as you can see here, this just maps the bubble sort program to those binary numbers there. But for Minecraft, this still isn't enough because obviously the CPU exists in Minecraft and it's made out of blocks. It can't understand text files. So we have to run it through one more program called a schematic generator. And what that does is it takes the binary input from the assembler and it converts it into a set of Minecraft blocks, which you can then insert into your world. Sorry, is that a question? Or? All right, moving along. So we have a CPU, we can run programs on it. Now we can run Minecraft, right? Unfortunately, it's not that simple because graphics processing on a CPU is really, really slow, on the order of millions of instructions to render a frame of Minecraft. And with a CPU clock speed of 1 Hertz, that's not going to get us anywhere. So we're going to have to build a graphics processor to get around this problem.
Maybe something just as a kind of a general question on the way this works. So I assume you are not playing around with the joystick and copying the zeros and the ones into Minecraft. So there is some way for you to automatically take a text file and upload it into Minecraft blocks to import like import blocks from a file.
Yeah, I mean, there's this mod called World Edit, which allows you to take a schematic, which is just like a small collection of Minecraft blocks, and paste it directly into the world. So this just means you can like upload a file essentially of blocks.
And the second thing, is there a Minecraft simulator that allows you to show things not in real time but speed up arbitrarily, or
I'll get to that later. I'll get to that later, yeah. So anyways, now we have the task of building a graphics processor, which we're going to need to take quadrilaterals in 3D space, like this, which have 4 coordinates, X, Y, and Z. And we also need a camera position and rotation, which is where the player is currently looking from. And we somehow have to take that and translate it into pixels on a screen. So this seems like quite the tall task. So how are we going to accomplish it? Well, first of all, we have to understand how do textures work. And they work using something called UV mapping. So suppose we had this polygon here in 3D space, and we wanted to map this checkerboard texture to it. What we can do is to the 4 corners of it, we can assign values called U and V, which are essentially coordinates between 0 and 1 on the texture. And then we can assign those same coordinates to the 4 corners of the quadrilateral. And now whenever we want to figure out the color of a pixel, say, for example, this one, we could apply some mathematics to find out what its U and V values are based on its position relative to the other, the vertices of the quadrilateral. And then using that, we can find out its position on the texture. And so we can see that that pixel there should be black. And then if we just apply this to all the pixels on the quadrilateral, we'll get our entire quadrilateral like that. So now we can get into how some of that mathematics works. First of all, the white circuit here deals with translation and rotation. So when you input a quadrilateral like this, you can see it has X, Y, and Z coordinates, but they're relative to the origin of the world, not to the camera. So you want to get it in a position relative to the camera instead. So first of all, you translate it so that the origin essentially becomes the camera position. And that's fairly simple. You just subtract the camera X, Y, and Z from each vertex X, Y, and Z. Rotation, on the other hand, is a little more complicated. We just have to feed it through that matrix. Just do a quick matrix multiplication. I'm not going to go into exactly how that works, but that just rotates the each vertex so it's in the correct position in front of the camera. Now, there is one problem that we have to deal with at this point, which is what if a quadrilateral is partially behind the camera, such as this one here? So suppose that black line there is where the camera is, or that's where Z equals 0. And then the areas of plus Z are in front of the camera and the areas of minus Z are behind the camera. Well, we're not going to be able to render a quadrilateral that's partially behind the camera like this. So we need to somehow turn it into one that's entirely in front of it. So we can take this edge by edge. Let's start with the first edge here. As you can see, both vertices are in front of the camera. So this edge is entirely in front of the camera, so that one's fine. Now we look at this edge here. As you can see, one vertex is in front of the camera, but one edge is behind the camera. So what we need to do is create a new vertex just in front of the camera on that edge, like that. And we also have to keep track of the new U and V values of that edge, since it's going to be somewhere else on the texture, obviously. So then moving along, we have that third edge there. Since both vertices are behind the camera, it's entirely behind the camera, so we don't need to worry about it. And then this last one, similarly to the second edge, you can see it's partially in front and partially behind the camera. So we can, again, create a new vertex right in front of the camera, and that finishes off our new quadrilateral like that. So here it is actually possible to get a triangle or a pentagon as well, and that's just dealt with by simply splitting it in half, and that gets you a quadrilateral. So moving on, now we have something that's definitely in front of the camera. We can actually project it to find out what its coordinates are on the screen. So that's essentially this process here. You just take the X, Y, and Z coordinates of each vertex, and you turn them into X and Y coordinates on the screen. I'm also not going to get into exactly how this works. It involves some dividing by Z. But the important thing to keep in mind is that now, since we have divided by Z, in order to keep textures consistent, we also have to divide U and V by Z, and then undivide them at the end. So that's projection. Now we have the coordinates of each vertex on the screen. So before we continue to render the polygon, it's important to get rid of polygons that we don't actually need to render, and this is called culling. So there's two types of this that we've implemented. The first is called frustum culling, which basically means if a polygon is entirely off the screen, here represented by the rectangle, you obviously don't need to render it since it's not going to show up. So this is fairly easy to check for. You could just check if all of the X coordinates are greater than the edge of the screen or less than 0, and similarly for the Y coordinates. And if they all are, then you can just ignore that polygon entirely. Then backface culling is slightly more complicated. Suppose you had a cube like this. You can see the 3 light green faces are facing towards us, so we're able to see them. But the 3 dark green faces are facing away from us, and therefore they're going to be covered up by other faces, and it's impossible for them to be seen. So we can actually detect this. And the way we do this is by always drawing polygons in a certain order. So as you can see, the 4 vertices of this polygon are arranged clockwise, 1, 2, 3, 4 in that order. And suppose this one is facing towards us. If we imagine rotating it 180 degrees in 3D space, so it's facing away from us, you can see that the vertices are now facing in the they're now in anti-clockwise order instead. They're going 1, 2, 3, 4 in the opposite way. And we can detect this using something called a dot product. We can just take the dot product of 2 edges that coincide at a vertex. And if the dot product is positive, it's going one way. And if it's negative, it's going the other way. So then we can just get rid of the one that we don't want. So this way we can get rid of faces that we know we're not going to render. So we're left with a face that we are absolutely sure is on the screen and we're going to render it. How do we do that? Well, we have all sorts of weird shapes like this at this point, and creating a circuit that can handle all of them consistently would be quite difficult. So it would be nice if we had something a little more consistent. And the way we're going to do this is by splitting them using horizontal lines into trapezoids and triangles. And a triangle is really just a trapezoid with one edge being of length 0. So they're essentially the same thing in the circuit. And what this means is we now have 3 shapes that are importantly consistent in how they are shaped. So now we can pass this into a circuit that renders trapezoids, which first of all splits them into rows. This is fairly self-explanatory. You just need to keep track of the starting and ending X of each row, as well as the U and V values of it. And then that feeds into this circuit, which splits each row into pixels, also fairly self-explanatory. And again, at this point, since we've been interpolating between the 2 edges, we know the exact U, V, and Z values of each pixel. So something that's also interesting about this part of the circuit is so far the entire graphics processor has been 16-bit, but here's 16 bits is no longer enough precision, so we actually need a 24-bit circuit here, which is why it seems bigger than the last circuit, despite essentially doing the same thing. So now we have our pixels, we have the U and V values of each. We just need to find their positions on the textures themselves. So how do we store the textures? Well, this is the entire texture file of the Minecraft in Minecraft, actually. You might be able to recognize quite a few of the textures. For example, the various blocks on top, and then we have numbers, items, and so on. So the 3D renderer can actually render any of these, but there's quite a lot of them. In fact, it's about 2 kilobytes in total. And this is stored in this thing called the texture ROM, or texture read-only memory. But again, this suffers from the same problem we talked about earlier, where if you have a very large memory circuit, it can take a very long time to read from it. So we're going to solve it in exactly the same way using a cache. This here is the texture cache, and it stores 16 textures, which is 128 bytes. And this just means that we don't have to be frequently fetching textures from the texture ROM. And then using the U and V values, we can figure out the color of each pixel from the texture cache. So now we can render polygons. There's just one problem that we haven't dealt with yet. And that's, what if we try and render a polygon and then another one that should be behind it? Currently, it'll just overwrite whatever that polygon was. So we need to somehow store information about how far away each pixel is. And that's done using something called a depth buffer. So this just stores 1 over the Z value of each pixel. And the reason we use 1 over Z and not Z is because this allows us to have more precision close to the camera, which is fairly important for avoiding visual glitches, but essentially it just stores how far away from the camera it is. And then there's 1 byte per pixel, or 8 bits, so that's 6 kilobytes in total. As you can see, it's a fairly large circuit as well. And so the way we interface with this is whenever we need to write a pixel to the screen or update its color, we just compare the current distance from the camera of that pixel to the distance from the camera of the new one we're trying to draw. And if it's closer to the camera, then we can overwrite it. If it's further away, then we just ignore it. So what this means is we can now render our polygons in any order and they'll always look correct. So that's our entire graphics processor, which is called the Absurdly Massive Operator on Graphics by Uwerta and Samiuri. Uwerta is just the username of the guy who actually designed this. So I didn't design this, I implemented it in hardware, but he's the one who actually did all the maths to work out how it works. So yeah, that's what we made. And now we can run 3D graphics within Minecraft. So we're almost done. There's just a few other bits and bobs that are necessary. And an obvious one is a screen, since obviously we need to be able to see what we're rendering. So this screen here is a 96 by 64 pixel resolution, which is not much, but it's enough to be able to recognizably, see Minecraft blocks if you strain your eyes really hard. Not only can it copy data directly from the graphics processor, like what was just rendered, it can also draw rectangles on the screen, and it can draw textures in 2D directly to the screen. And this is used, for example, if you need to create an inventory or graphical user interface or some kind of def screen, for example. We can just copy those textures directly to the screen. So as well as that, we have 256 bytes of world RAM. Now, what this does is essentially stores the world. So in case you don't know, the world is 8 by 8 by 8 blocks, so it's pretty tiny. And there are 16 block types, so each block is 4 bits. So that's a total of 512 times 4 bits, which is 256 bytes. And the way you actually access this is that the CPU can send X, Y, and Z coordinates to it. And then it can either access the block at that location or set it to a new block, for example, if you place or break blocks. So that's the world RAM. Then we have the world to mesh converter. This is a circuit directly adjacent to the world RAM. And so far, I've talked about the graphics processor handling quadrilaterals, but obviously the Minecraft world is made of blocks, not purely out of shapes. So what this does is it handles turning blocks into shapes. And for example, for that green block there, you can see it's turned it into those 6 faces. But it also runs some other optimizations. Like, for example, if 2 blocks are next to each other, the face in the middle isn't going to show up since the other block is obscuring the view. So it just ignores that face entirely. Similarly, it also renders specially shaped blocks, such as saplings and chests, which aren't exactly a full block. For example, a sapling is shaped like a cross between 2 corners of the block, and a chest is just slightly smaller than a full block. So it also deals with creating faces to render those. And finally, the controller. This is fairly self-explanatory. It's a controller. You use it to control the game. And whenever you push any of the buttons on it by stepping on it with your player character, it'll just send the signal to the CPU. There's a queue which stores the most recently pressed controller inputs. And then whenever the CPU processes a new frame, it just reads all the inputs from that queue. So now we have all the hardware done. We need to talk about the software side of things, since we still have to program, all the game mechanics of Minecraft. So like I mentioned before, this is done in assembly, and there's quite a lot of code. That's just the first 10% of it. So yeah, unfortunately, assembly code is not very nice to write and especially difficult to debug. But yeah, this handles quite a lot of things. So first of all, we have game mechanics like player movement and collision. Then we have raycasting, and this is just an algorithm that is used to tell which block a player is looking at, for example. So you know where to place or break a block, or where to show the highlights that the player is looking at a block. Then we have breaking and placing, which is used to modify the world. Item entities as well. These can't be handled in the same way as other blocks, since they have their own physics and they're rendered differently as well. So they need their own set of code. And random ticks, which is things like leaves decaying, saplings growing, grass spreading. The way that works is the CPU reads in 3 random numbers, which correspond to an X, Y, and Z coordinate. Then it checks what that block is. And if it's a block that can be random ticked, for example, leaves or grass, then it'll update it as necessary. Then we also have the user interface, which involves things like the hotbar and inventory, crafting and smelting, and chests, and so on. And it also has to deal with things like the def screen and drawing that to the screen. So
did you write also an interpreter that allows to execute assembly programs without uploading them into Minecraft?
Yeah, we developed an emulator that also includes the graphics processor. So we tested the entire thing in an emulator before actually running it in Minecraft, of course, since it's just much easier to debug that way.
What source of randomness in Minecraft do you use to get those random X, Y, and Z coordinates for the random ticks?
So in normal Minecraft, there's actually random things like dispensers and so on. But in the special server, which I'll talk about later, that doesn't exist. So we have to use pseudo-random number generators instead. So I think I used a 16-bit Fibonacci shift register, which, I mean, it's not terribly random, but it's good enough for, seemingly random numbers. At least for running Minecraft in Minecraft, it was all right. All right, so that's everything the program does. As you can see, it's quite a lot of stuff. So in total, it comes out to 7.7 kilobytes. Now, the astute among you may have noticed a problem here, because earlier I mentioned that the CPU had 4 kilobytes of program memory, and clearly 7.7 kilobytes is not going to fit into 4 kilobytes. So we have to somehow upgrade the memory capacity of the CPU. And the way we're going to do this is using a technique called bank switching. So suppose we have the CPU here, and instead of having just one program memory ROM attached to it, we hook up 2 banks of 4 kilobytes each. Now, since the CPU can only access 4 kilobytes at a time, at any given time, only one of the banks is actually being read from. So, for example, it defaults to bank 1 when you start the program. But then whenever we need to, for example, if we're trying to access a subroutine that's in bank 2, we can just switch the bank. And then the CPU will be reading from bank 2 instead. And we can go back and forth as many times as we need. And what this means is that we've essentially upgraded the memory capacity of the CPU without having to upgrade the CPU itself, which is really convenient. And 4 plus 4 is 8, so 8 kilobytes is enough to load the program. So we're also set in that regard. And at the end of all that, we have the finished build here. So it's a bit of a mess due to how many different colors there are, but as you can see down there in the corner, we have the CPU. Then we have the graphics processor there. The depth buffer underneath the screen, which is right there, and then the world RAM there, and the controller on top. So that's the finished build, and there is unfortunately one thing that we haven't considered. So as was mentioned a while ago, Redstone is fairly slow. 1 tick is 0.1 seconds, which might not seem like a lot, but when you have a lot of ticks, that adds up quickly. And this is particularly noticeable for the graphics processor, because if we have hundreds of ticks per row of pixels, which is simply due to all the logic gates required to calculate it, and then we have many rows in each quadrilateral, and then we have hundreds of quadrilaterals in each frame of Minecraft, well, that's going to come out to quite a long time. And unfortunately, running it at a few days per frame is not going to cut it. So we have to somehow figure out.
That's why modern GPUs are highly parallel.
Sorry, could you repeat that?
I'm saying that's why modern GPUs are highly parallel.
Yeah.
Maybe that's your next project, training a neural network in Minecraft.
Well, I'll get into that later. So the way we solve this is with something called Minecraft High Performance Redstone Server. And this was what was designed by the third member of the team, who goes by the username Stack Doubleflow. So suppose we have this circuit here, which is pretty simple. It's just a lever with 2 repeaters, some redstone wire in the middle, and a lamp on the other side. So the naive way of doing this, which is how Minecraft implements it, is just whenever a component changes state, it tries to update all the components around it based on what its new state is. So for example, if you activated this, the repeater would power the first dust, and then the first dust would search all around it, would find the second dust, and then that one would search all around and find the third dust, and so on. Unfortunately, this is really inefficient when you have a lot of redstone components, especially a lot of dust. And the problem is even worse when dust is turning off, since it essentially has to pass through every signal strength between 15 and 0. So you'll essentially get a number of updates quadratic in the size of the circuit. And that's really bad. So we can't simply speed up the game and expect to get a very high frame rate. Instead, we're going to have to somehow redefine how redstone works entirely, or well, implement it in a more efficient way, I mean. And this is done using something called the redpiler, which is basically a compiler for redstone. So as you can see, this redpiler graph here is the same as the circuit above. And in these graphs, each node corresponds to a redstone component, and the edges are just the distance between them. So what this does is that when you compile the redstone, each component will just do a breadth first search behind it to find other redstone components and how far away they are, and it'll just add them to the graph like that. And then when you actually run the redstone circuit, it doesn't have to, search around it for all the updates again. So it's much more efficient since it only has to process a graph, which is much more friendly to a computer than Minecraft blocks. But you might have noticed that even this graph isn't particularly well optimized, because there's a bunch of leaf nodes there, which are redstone wires, and they're actually irrelevant in the redpiler graph, because as you can see, the redstone repeater takes its input directly from the other repeater, and the wires are pretty much just there for decoration. So we can optimize this further and get rid of all redstone wires in the graph entirely. So that circuit on the left there has been optimized to that very simple graph on the right. So when we flick the lever, it only has to update 4 nodes in total. And this is very efficient. In total, this gets a speed up of about 20,000 times when running my circuit, which corresponds to a frame every 10 or so seconds rather than 3 days. So that's still not great, but it's bearable for long sessions of gameplay. So now that we can run things in somewhat real time, we're finally done. It works, almost. Unfortunately, bugs occurred, as they do in most areas of computer science. Here, the world simply failed to generate properly. Half of it was cut off. Similar problem occurred here. This one was a particularly spectacular glitch where all the air blocks in the world got replaced with chests. That one also took quite a long time to render. But yeah, and we finally have one that worked. Not quite. As you can see, there's a couple faces missing here. That one was particularly frustrating to debug. But I somehow plowed through it all. And at the end, we have our first functional render right there. And I was unbelievably happy when I saw this. Oh, wait, we're not done yet. So all the other features that I mentioned earlier, I'm not going to waste time talking about them. If you want to see them, you can check them out on my YouTube video, which is linked right there. I also recommend just watching my YouTube video, please. I'm just kidding. So now that it's done, what's next? Well, I mean, we have a graphics processor. It's not specific to Minecraft. It can render any 3D graphics, really. So the obvious next choice would be to run Doom in Minecraft, right? So for those of you who don't know, Doom is a first-person shooter from the 1990s, which has become notorious for supposedly being able to run on anything. I mean, I've heard of Doom on a calculator. I've heard of Doom on a pregnancy test, although I think that one might have been faked. But yeah, we can. We're now able, theoretically, to run Doom in Minecraft. We just need to reprogram the CPU and, come up with graphics that look vaguely like Doom. So that's one possibility. Another interesting project that we could work on is Redstone in Minecraft. Because if you remember from the start, Redstone isn't actually that complicated. There's not that many blocks that we need to implement. So it is possible to, try and implement that in assembly and actually run Redstone in Minecraft. But there's another reason this is so intriguing, and it's because of this machine here, which was designed by a user called Lies Live. And believe it or not, that tiny little machine there is a Turing machine. It can theoretically, given enough time and memory, run anything. So if we were to create Redstone in Minecraft, theoretically, it might one day be possible to run Minecraft in Minecraft. Thank you for listening.
All right. Does anyone in the audience have questions for Sam? Yeah, William?
Yeah. I might have missed this in the beginning, but what instruction set does Minecraft understand, or did you make your own?
Well, Minecraft and Minecraft is just a program. The CPU itself.
The CPU.
The CPU uses an instruction set that I designed myself for it. So it's loosely based on RISC instruction sets or reduced instruction set computers. But the specifics of it, I designed myself in order to, have something specific to my CPU. So, for example, I don't want to just copy an existing instruction set because it might have features that I don't need to run my programs. So, yeah, I designed it myself.
Thanks. And one more question.
Yeah.
In terms of, can you explain again how you made the Redstone compiling faster? How did you speed up?
So you mean MCHPRS? You mean this bit?
Yeah. So is it like the Minecraft game, you reprogrammed it to do this sort of graph generation?
Yeah, so I didn't actually program this bit. That was done by another member of the team. So I'm not entirely sure on all the specifics, but I'm pretty sure the way it works is, it's basically a server that's programmed in Rust. And for the most part, it runs like normal Minecraft, but you can activate the red piler, and that takes all the Redstone components in the world and compiles them into a graph. And then whenever you try and run a Redstone circuit, instead of running it the way Minecraft normally would, it uses the red piler instead, which is much more optimized for running Redstone. And then it just sends you the result of what the red piler graph calculated. Does that answer your question?
So the ticks are much faster, like, so basically.
Yeah. Instead of running at a fixed tick rate, it also runs as fast as your real life computer can handle it, which is really convenient as well.
So you can basically disable the standard Redstone interpreter that Minecraft runs?
Yeah, well, I mean, not in normal Minecraft, I think, because what Stack Doubleflow did is he reprogrammed an entire Minecraft server from scratch. So it has its own Redstone implementation in this way, rather than the standard Minecraft one.
I see. Thank you.
You're welcome. Any other questions?
Holly from the chat says, how much of the hardware did you design yourself and how much was already designed before you started?
That's an interesting question. So, so basic things like adders and single cells of memory, for example, those at this point are fairly standardized designs because I mean, the Redstone community has existed for a very long time. So we've discovered essentially the optimal configurations for small circuits like that. However, once you start getting into bigger circuits like components of a CPU or bits of the graphics processor, those tend to be very rarely optimized. So you have to build your own ones in order to get them to be as efficient as possible. So yeah, I mean, most of the hardware is either my own design or a combination of smaller circuits designed by other people with wires in between.
So I'm wondering, it seems like a lot of the constraints that you're grappling with are the constraints that people had when they were doing the early consoles, say the Atari consoles in the 80s and things like that, where they also had a lot of, fairly small memory. So do you know if there are similarities between the designs in Minecraft and these designs?
Well, I mean, other than the amount of memory, for example, they're not actually that similar. So, for example, I think most CPUs like from that era used accumulators, for example, whereas my CPU doesn't have an accumulator. It instead just has a set of general purpose registers. And it also has things like a call stack and a stack pointer that I'm not sure if they had back then. But on the other hand, those CPUs, since they worked in real life with electricity, they had clock speeds in megahertz rather than hertz. So they could actually, handle more program memory as well. Like, for example, I'm thinking of the Commodore 64, even though it was also an 8-bit CPU back then, it could handle up to 65 kilobytes of memory.
That was my second computer, by the way. I started with the big 20. Got 4K.
Right, do we have any other questions?
There is a question someone asked on Zoom, how did you learn all of this?
Oh, how did I learn all of this? So, well, I'm entirely self-taught since I'm still in school. So most of it is from the internet. And also from going onto this Minecraft server called Open Redstone Engineers, where there's loads of wonderful people that are willing to teach you how, things like CPUs and binary and stuff works. So I learned quite a lot from there, and also just from doing my own research on the internet. Wikipedia is surprisingly useful sometimes.
How long did you work on this project?
So if you so actually I designed the CPU before considering the possibility of running Minecraft in Minecraft. So that was about 7 months. I did that last year. And then earlier this year, I think in February, Uwerta came to me and said, I have this graphics processor design in assembly. Do you want to run Minecraft in Minecraft? So I took him up on his offer, and that was another 7 months, I think, of work. So in total, about a year and a bit. Yeah.
That's incredibly impressive. And I think along the way, you kind of learned the contents of probably 5 computer science courses.
Yeah.
Nice perspective is very impressive. I have a question. Wait, sorry if you already answered this, but did you like automate the building of certain parts of things, or did you like literally manually place each block?
Right. So it depends to what extent you mean automating, because obviously I didn't manually place each block. There's programs that like can take a component you've already built and repeat it a certain number of times in a certain direction, for example, or move components around and things. But I did like manually decide, where to place each component, like each adder or each memory cell, since I think there has actually been a project to create a Verilog compiler for Minecraft that compiles, actual logic gates and stuff into Minecraft blocks. But that suffers from being horribly inefficient, since it's very hard to optimize, especially for a 3D environment such as Minecraft, and get everything to work so efficiently. So it's for this case, it was better off just to build everything by hand, other than, of course, stacking components and stuff.
How long and how did you decide on the thumbnail for the video? Because I know that if you want something to go viral on YouTube, the thumbnail is like one of the most important parts.
Yeah. Well, I've been in communication with some more popular YouTubers for a while, who are also Redstonists themselves. So essentially, they decide the thumbnail for me. I just, like gave some general comments on what I wanted it to look like, but yeah, the thumbnail is their design. I've credited them at the video somewhere as well for it.
Jimmy, I have a question. Yeah, so how did you, decide when you make some circuits and it is optimal enough for you? Like what's the, yeah.
That's an interesting question. Generally, I try and, plan it in advance to make sure it's optimal from the get-go. So I try not to just get into building things, because then you might run into the problem that later on you'll realize, I could have made that more optimal in the first place. And rebuilding stuff you've already built is much harder than just planning it in advance, making sure it's optimal, and then building it. So in fact, I think we spent about a month and a half just designing the graphics processor and running, emulators and doing all the math before we actually placed a single block in Minecraft itself. And that way we already had the entire design. We knew it was optimal. We knew it was going to work.
You know or have an estimate for how many blocks are in like the whole system?
That's something that would be really easy to check, but I'm not actually sure. I think it's in the hundreds of thousands for Redstone components. For blocks, if you include all the blocks that the Redstone components are placed on, maybe 1 million. But yeah, I'm not 100% sure about that.
Max from the chat asks, was more time spent on actually thinking and doing the math, or more on trial and error and troubleshooting?
So initially we did a lot of math, of course, but troubleshooting was probably the biggest, time sink of the project, especially for the graphics processor, because it's simply so big. There's so many components in it. And if something goes wrong, you have to, check every single one until you find the problem. So it could take many hours to solve a single bug in that. So yeah, I think troubleshooting took a lot more time than just thinking and planning it.
Oh, I have a question. Yeah, somewhat along the same line, but how did you debug something like this? You can't really just like step through a debugger and see like the line of code that's causing the problem.
Well, you could do something better. You could step through the build itself and see all the, the bits and memory and stuff. So MCHPRS does have this very useful feature where you can step by a single redstone tick, for example. So you can advance all the logic gates by one state and see what it is, like the outcome of that. And using that, it's generally much easier to pinpoint the problem, since you're essentially just stepping through hardware instead of stepping through a program. But yeah.
If you really wanted to, could you build this in survival mode?
Yes. If you really wanted to, you could, but I don't recommend it, of course.
You have a question. Maybe I just end with a potential suggestion to you.
Okay.
If rather than continuing on in Minecraft, maybe one more field you might want to teach yourself and look into is biology, and in particular, DNA, RNA, and there have been works. Even the COVID vaccine, to some extent, works a little bit like a bit of a program in some sense, and there have been some works of trying to kind of build like a kind of biological nanobots that go and fix. So that could be an interesting field for you to explore. And I don't know if necessarily more useful than Minecraft, but it could interest a different set of people.
Right.
All right, thank you so much, Sam, for coming to talk to us. It's been very
Thank you for having me as well. This was a great opportunity. Thank you so much.
Yes.